Out here in the desert, water is a little scarce, especially when it comes to clean, drinkable water. This problem affects everyone in Tucson, but contaminant levels are much higher for Summit County in southern Arizona. These chemicals, commonly known as forever chemicals, are found in many everyday products and have made their way into water resources in Tucson. The largest perpetrator in southern Arizona is the nearby Davis-Monthan Air Force Base, who used to dump firefighting foams riddled with PFAS about the area. The existing Tucson Airport Remediation Project TARP treatment plant does not meet the EPA's maximum contaminant level for PFAS, so it is allocated into the Santa Cruz River.
Why does this matter? Studies link PFAS to serious health risks, including cancer, liver damage, and immune system disorders. And these impacts have been seen directly in Southside populations. The reallocation of TARP water to the river instead of to homes leaves an urgent need for clean water for 10,000 households in Summit County. The Real Water Treatment Plant addresses this demand. We will walk you through the process of how our facility effectively removes PFAS and other contaminants, protecting the health of thousands of underserved residents in southern Arizona.
Per and polyfluoroalkyl substances, also known as PFAS or forever chemicals, get their name from the incredibly strong chemical bond between carbon and the very electronegative fluorine. The tail of the molecule consists of a carbon backbone with attached fluorines, making it extremely stable, electronegative, and hydrophobic, where they are resilient against most degradation methods. At the end of this exists the head group, which is hydrophilic. Our target treatment molecules are the long-chain PFOS and PFOA with the functional head groups of sulfonic acid and carboxylic acid, respectively. We chose these because the Davis-Monthan Air Force Base has addressed these as the primary components of the industrial products that have been dumped in the area in the past. PFAS removal from water is achieved by adsorption. Adsorption is a process by which atoms, ions, or molecules from a gas, liquid, or dissolved solid stick to a surface called the adsorbent. Molecules that are adsorbed onto the surface are called the adsorbate. In our case, the adsorbate is the PFAS molecule, and the adsorbent is the granulated activated carbon, also known as GAC particle. As contaminated water flows through the GAC bed, adsorption kinetics cause the PFAS to stick to the surface, leaving the treated water behind. The main driving forces behind PFAS adsorption are electrostatic and hydrophobic interactions, which are types of physical adsorption. Electrostatic interactions are more relevant for short-chain PFAS removal. The negatively charged PFAS molecules attach to the positively charged GAC particles due to electrostatic attraction. Hydrophobic interactions are best for long-chain PFAS removal, where the nonpolar tails prefer the carbon surface over water. Hydrophobic aggregation leads to micelle formation, which is a spherical structure with hydrophobic tails clustering inward and hydrophilic heads facing outwards.
The Real Water Treatment Plant is split into 4 main unit operations: the sedimentation zone, a UV AOP process, PFAS removal, and backwash. This system takes inspiration from the Marana Picture Rocks Water Treatment Plant and the TARP Water Treatment Plant. The plant is modeled to produce 1.2 million gallons per day to serve Summit, Arizona and the surrounding communities. It features an advanced oxidation process, AOP, to remove another harmful contaminant, 1,4-dioxane. The plant utilizes GAC, particularly 2 sets of lead and lag GAC contact vessels to remove the PFAS via adsorption.
To satisfy the demand of 10,000 households, these ground well pumps will supply 1.2 million gallons of water per day and sustain an adequate pressure gradient for the whole system. Immediately following the pumps comes the sedimentation zone. This zone is the first defense against large particles which would otherwise damage and diminish the efficiency of downstream processes. Since this is a freshly drilled ground well on a new plant, there will be little to no large particles present. However, as the well ages, more sediment is bound to be pumped through. This requires overly cautious sizing of desanders and clarifiers that can handle a high-density slurry. The clarifier is a secondary step to capture the smaller particles that creep through. These nanomaterials that resist the sediment efforts are pushed downstream to equipment that is now protected from damages against sediment.
Once sediments are removed, the water moves to the UV Advanced Oxidation Process, or AOP. This stage is crucial for breaking down a harmful contaminant known as 1,4-dioxane. 1,4-dioxane is an industrial chemical that is the byproduct of products such as hand sanitizers, cosmetics, and dyes. It is commonly found in the groundwater throughout the United States. It is a carcinogen, posing huge health risks to communities. Currently, there is no federal regulation on the MCL of 1,4-dioxane, only a health advisory from the EPA to be enforced at the state level. The real water treatment plant is modeled to remove the contaminant down to a level of 0.1 parts per billion after treatment. The treatment of 1,4-dioxane involves the use of a powerful oxidant, hydrogen peroxide, and UV light. The degradation of 1,4-dioxane begins with the UV-induced decomposition of hydrogen peroxide into reactive hydroxyl radicals. This leads to rapid breakdown into intermediate products, which are further oxidized into non-toxic byproducts such as water, oxygen, and carbon dioxide. This treatment step ensures that by the time the water reaches consumers, it is free from the dangerous chemical 1,4-dioxane.
Now that we've removed sediments and treated 1,4-dioxane, it's time for the crown jewel. PFAS removal using Calgon FilterSorb 400 GAC, also known as Calgon F400. Each of the 4 GAC tanks have 20,000 pounds of GAC in them. Inside of the tanks is a packed bed consisting of the F400. PFAS is removed by PFAS adsorbing onto the carbon surface. However, over time, the carbon becomes saturated with PFAS, meaning it can no longer capture contaminants effectively. This is called breakthrough, and when it happens, the carbon must be replaced. To ensure continuous water treatment during GAC turnover, our system operates in a parallel lead-lag configuration. The lead tank initially captures most of the contaminants, while the lag tank remains relatively unused until breakthrough occurs. As the lead tank reaches exhaustion, meaning its mass transfer zone, MTZ, has fully progressed through the bed, the lag tank becomes the new lead, and a fresh bed of GAC is introduced as the new lag. This staged approach effectively extends the empty bed contact time, EBCT, and slows the progression of the MTZ, maximizing GAC usage, delaying replacement, and reducing operational costs. Maintaining GAC is simple, only requiring infrequent backwashing to loosen up solid particles that get trapped and inhibit PFAS absorption.
Our system design includes a backwashing operation to maintain efficiency. During backwashing, the piping manifolds to the GAC contactors are adjusted, allowing water from the ground well pumps to flow in the reverse direction through the beds. This dislodges accumulated sediment, which is then collected in the backwash tank. After filtration through bag filters, the water can either be reintroduced into the operational flow or removed via vacuum tanker. Backwashing is essential because it prevents sediment buildup and reduces head loss through the GAC contactors. Lowering head loss decreases the pressure required from the ground well pumps, improving overall system performance.
Rather than continuously purchasing new GAC media every time it reaches the end of its life cycle, the carbon can be reactivated. To optimize our system financially and environmentally, we switched to the use of third-party GAC reactivation instead of continuously purchasing new GAC and sending the spent media to the landfill. So how does this reactivation work? The reactivation process volatilizes and destroys the adsorbed contaminants at high temperatures and restores the GAC to a near virgin state so it can be reused. Reactivation results in a full removal of PFAS compounds and destroys greater than 99.9% of PFAS. In our first year using the new media, we slashed carbon dioxide emissions by over 740 kilograms, cutting our impact from 831 kilograms down to just 88 kilograms. That's nearly a 90% reduction. Additionally, the media optimization reduces waste to a landfill or incinerator by 90%. Using reactivated GAC will also reduce our annual costs. Reactivated media only costs 30% of the original media cost.
When looking at our entire annual operations, this switch results in 63% cost savings. That's a massive reduction in operating expenses. We began with an initial investment of around $11.4 million. Each year, the plant generates $7.6 million in sales, with total annual expenses around $5.26 million. This results in $2.7 million in net earnings and $2.1 million in actual cash flow. We break even by year 10 in present value terms after applying a 10% discount rate. This isn't just a treatment plant, it's a commitment, a promise to the community of Summit, Arizona that it's a human right to have clean water.
Water connects all of us, and at the Real Water Treatment Plant, we're not just filtering out contaminants, we're restoring trust, health, and hope.
Because when clean water flows, so does opportunity.
Together, we're making the future brighter and cleaner for future generations to come.
This is real change.